Welcome everyone to today's Saturday session of the UKZN Mathematics Club. This is actually our first session, and so we're piloting the program to expect a launch next year where we run both online as well as physical programs at UKZN. So there's a lot for you to look forward to. So the aim of these sessions is to, number one, expose you to the beauty and the fun that one could have with mathematics. We would be doing this by learning specific mathematical content, but also looking at problem-solving type questions. So one of the motivations behind this session is to also prepare students for SAMO, etc. This was something that Professor Poobalan Pillay had led for many years at UKZN. So we're marrying these two concepts. And today's session will be led by Prof. Poobalan Pillay, where he will be teaching you some geometry, but also we'll have time to look at various types of questions pertaining to the concepts you will learn today. Joining us today is also Dario Trinchero. He is a PhD student at Stellenbosch University, and he currently works in topological quantum field theory. Hi, Dario. Has switched off his video. But,
sorry. Hi. Very, very kind of you to have me here. Thank you.
Wonderful. So I see many of you are introducing yourselves in the chat box. That's wonderful. Please continue to do so to tell us where you're from, what grade you're in. Of course, today's session is aimed at the seniors. And so we were aimed at, this is aimed at grade 10 to 12 students. However, if you're not in those grades and you're still here, then welcome, because you're definitely going to be able to learn. So I'm going to tell you a bit more about Prof. Poobalan Pillay. So without revealing his age, I'm going to tell you that Prof has lectured, I believe, from 1967 at the University of KwaZulu-Natal, formerly known as UDW. So he is currently an emeritus professor at UKZN. Prof has an extensive CV, and he has been, well, apart from doing mathematical research, working in ring theory, etc., he has also been involved with AMISA, which many of you might be familiar with, for more than 30 years. He was external moderator for Umalusi, for the National Mathematical Grade 12 papers since 1990, I think up until 2017. He's involved in a number of training programs where these programs train teachers who train learners for Olympiads. He's co-authored several books. And in particular, he has authored a training manual for the South African Olympiads. This book is available, and actually you're going to hear more about it in today's session. In addition to that, he's also completed a second edition of the training manual, where there's about 600 problems that has been compiled in it. So I can tell you that we're going to have lots of fun today, and you are in exceptional hands with the work and the content, and with Prof. Poobalan Pillay. So I'm going to hand over to him. But just one more thing before I do. Remember, we have a Q&A and we have a chat box. Please make use of both of them. If in particular you have a question that you would like us to ask Prof. Poobalan Pillay today, you can put it in the Q&A. It'll help us keep track of it, and you can keep comments for the chat box. So let's have fun. And I'm now going to hand over to Prof. Pillay.
Thank you very much, Serene. Thank you for that introduction. And welcome to all those who have taken the time off on a Saturday morning to join us, because obviously you did it because you love mathematics. Well, let's get straight into the event of the day, and that is to do a little bit of geometry. Now, I'm going to start with the very first lessons that you learn in geometry, and I'm going to build it up to rather advanced problems. So we will go through this step by step. The way I've structured is I've chosen the problems and then decided on what the theorems are which are associated with it. So I'll do the theory before doing the problems, so that when we do the problems, you will already be, hopefully, be acquainted with the theory itself. All right, so let's start straight away with the triangle. I'm not going to do parallel lines and alternate angles. I'm pretty sure that you know about those things. And also that vertically opposite angles are equal. All right, so we will assume those early results. But as far as the triangle is concerned, one of the first things you learn about a triangle is that the angles of a triangle, they sum to a same number, no matter what kind of triangle you have, thin, tall, short, they all add up to 180 degrees, a very remarkable result. And let's see why this is so. But even before that, before we actually explain why that happens, I'm going to do what I call the flag theorem. And you'll see here, you've got a flag which is kind of sleeping. It's a triangle with one arm extended. All right. So when you extend that arm, there is an angle that is created. And that angle is this one here. Okay. It's called an external angle. There are quite a lot of external angles whenever you extend or produce any of these lines. But an external angle, there are two angles which are opposite it. In other words, there is one which is next to it, adjacent to it, and then the remaining two angles. The first theorem we're going to do is to prove that when you add these two internal opposite angles, you call them, right, you will get this external angle. The external angle of a triangle, exterior angle, is equal to the sum of the interior opposite angles. Now, why is this so? Well, to prove this, you can't prove it as it stands. You have to do a construction. In other words, you have to create some new line in this. And you can see what I've done in red is I've constructed a line, but this line is just not any old line. It is a line which is parallel to this. So I'll construct a line which is parallel to the opposite side. All right. Now, the moment you do that, then the X and the Y that I've spoken about earlier, now you can see a Z angle featuring here. In other words, these are alternate angles and they are equal because these lines are parallel. And you can also see an F angle here. There's your F. And the F angles give you what we call corresponding angles. So this angle here is equal to that. And now you see that the original angle has been split two ways, and the full angle is the sum of these two angles, X plus Y. So that proves this fact which I spoke about earlier, that the exterior angle is equal to the sum of the interior opposite angles. Now this
Professor
also,
Pillay,
yes.
Just one thing I wanted to also add there is if we only knew, for example, that the sum of the angles in a triangle was 180 degrees, we could surely also derive it just from that, right? Because we could see that our remaining angle in the first triangle you drew is 180 minus X minus Y, and then using the sum of the angles along the straight line.
Yeah, well, okay, that's good. I was just about to come to that.
Sorry, I jumped the gun.
Yeah, so this is we prove this theorem first because from there we can get the sum of the angles. If I call this angle Z, the three angles, if I call it Z, and earlier on we said that X plus Y plus Z is 180, and as Dario pointed out, they are actually all angles on a straight line, X plus Y plus Z. So that is why the sum of the angles of a triangle is the sum of the angles of these three angles, which are all now sitting on a straight line, which is 180 degrees. So this also proves that the sum of the angles of a triangle is 180 degrees. Okay, so yes, Serene.
Just a non-mathematical comment. I was wondering if we could zoom in on the page a bit. So next to the 100% on the bottom right, you've got a plus sign. If we make it bigger, I think it'll be easier for students to see.
Oh, I see. All right.
Yeah.
Thank you for that.
I think you need to switch over from pen. Yeah.
Oh, yes. Thank you. These are the kinds of things that I need to know. Oh, all right. Okay, thank you very much. Okay, it's gone a little bit distorted now, but I'm not going to go over that again. But thanks for that. Thanks for telling me how to do that.
Okay.
I really appreciate that. These are great pieces of knowledge. Okay, now let's get on now to congruency. I'm going to enlarging the page. Let's just get this thing out here first. All right. So there we are. Thanks, Hari. Okay, now congruency. What do we mean by that? Two triangles are congruent if they are identical in every respect, right? Now, what do you mean by that? It means that it's just as if you cut out one triangle and place it somewhere else. In other words, it's just a replica of another triangle. And then those two triangles are said to be congruent. They are equal, but we use the word congruent. Now, in any triangle, there are 6 numbers which are associated with them. The 6 numbers being the 3 angles and the 3 sides. All right. So you got the 3 sides are 1, 2, 3, and the 3 angles, which give you 6 numbers. All right. Now, if 3 angles of one triangle or 3 numbers, right? We will say what these are in a moment. If 3 numbers of one triangle are the same as the corresponding 3 numbers of the second triangle, then all 6 numbers are the same. Now, that's a very beautiful result. In other words, to get 2 triangles to be exactly the same, you don't have to show that all 6 numbers of one triangle are equal to 6 numbers of the other. You need to show only 3 numbers of one triangle are equal to 3 numbers of the other. Once you do that, then you can conclude that the remaining numbers are the same because they now become identical. They are now congruent, right? So now the question is, which 3 numbers? Do you take any 3 numbers? There are 3 sides and there are 3 angles. So okay, so there are 3 sides and there are 3 angles. So which 3 of these numbers will allow you to make the conclusion that all the 6 numbers are the same? Well, the first one is all 3 sides. If all 3 sides of one triangle are equal to 3 sides of another triangle, then you can conclude that these 2 triangles are congruent. So sorry, I'm just going to be a little bit sloppy here. So if you know that the 3 sides of one triangle are equal to 3 sides of another triangle, then like if those are the same, those 2 sides are the same. When sides are equal, we put strokes, but don't use the same strokes for different sides. So you got this side is equal to that side and so on. Now you can make the conclusion that all these 6 numbers are the same. So you can conclude that that one is the same as that one. These are conclusions now. And that one is the same as that one. And that one is the same as that one. All right. Now we said corresponding. What that means is that there is one of the angles of this triangle equals one of the angles of this triangle. So, but the sides and the angles of a triangle come in pairs. Now let me explain that. If you've got an angle, there is only one side opposite it. So that side and this angle together constitute a pair. So if we are talking about the angle that corresponds to this side, then it is that angle. And the angle that corresponds to this side is that angle, and so on. All right, so they come in pairs. The angle together with the side opposite. So that is how you will see which angle corresponds to another one in the other triangle. The second condition is this thing here. When you read it, you see it's as if it's two sides and an angle, but in fact, it isn't two sides and an angle. It's two sides and an included angle. So what happens here is that okay, so if you have just pardon me, I'm not very good in this thing. So there it is. If you got these two sides, then the angle included by them is the angle like this of one triangle equals two sides and the same included angle of another triangle, then you can conclude these two triangles are congruent. They're identical in every respect. In particular, you can say the remaining three numbers are the same. Okay, so so that takes care of that. And then finally, well, not finally, you have a case where the angle need not be included, right? And this is called the right angle, hypotenuse, and a side. Now, in this case here, the kind of triangle that we're looking at is we're looking at a right angle triangle. In other words, a triangle with one of the angles equal to 90 degrees. Okay, like this. So here, you don't have to have two sides in an included angle. You can have a non-included angle. Namely, you have to have the hypotenuse and then one side and the right angle. The right angle is already there, one of them. So you need to have just two other properties. In this case, you can have two sides. You can take any two of these sides, right, together with the right angle. If you have that situation, then these triangles are still congruent. It's the only exception to two sides and included angle. So this is an exceptional rule. That is why it's isolated as a separate rule altogether. And of course, you have two angles and a side, all right? And there too, you have to be a little bit careful that the angles and the side, they must correspond. In other words, the sides, once you know the sides, the angles, the two angles must be sitting on that side. Like this one here, the two angles must be sitting on the side. So those two angles must be the same. And then you will have that the two triangles, together with the side, then those two triangles are congruent. Right. One of the things that is missing is three angles here, you will see. All right. If you have three angles of one triangle are equal to three angles of another triangle, they are not necessarily congruent. Right? And it's very easy to see that. All we have to do is to take a photograph of the triangle that we have in question, and you will have a sort of smaller picture inside here. Maybe I'll just do it like that. And you will see, sorry, it's not very clear, but you'll have a small triangle sitting inside there. They've got the same angle because when you take a photograph, the angles don't change. But the triangles are not congruent because they have different sizes. All right, so much for congruency. It's an extremely important concept, this question of congruency. And we will use that now and several times to prove geometry. So you have parallel lines, you have the sum of an angles of a triangle, and you have these four conditions which make the two triangles identical in every respect. All right, so let me... Now, I'm now going to speak about isosceles triangles. Isosceles triangles are special triangles where two of the sides are the same, right? So if you've got two sides are exactly the same, then you call such a triangle an isosceles triangle. Now, I'm sure all of you know that when you have this situation, then it's always true that two angles are also the same. Not any two angles, but the angles which are opposite these sides, right? this angle which is opposite this side, this angle here is equal to this angle here. Right? But this is a theorem. We don't know that. Right? If you know that the two sides of a triangle are equal, how do you know that these two angles are exactly the same? Or for that matter, if you know the two angles are the same, how do you know that the sides opposite them are the same? How do you know that? Right? You can't just say it. You can make that as a conclusion. That becomes a theorem in geometry, where you have to prove it. And the way to do that is in an isosceles triangle. The beautiful thing about an isosceles triangle is that you can cut it down the middle. You can slice an isosceles triangle down from this vertex where the two sides are equal, where they meet, right? And you could split it down. But so how do you split it down? You can do any one of three things. You can either join this point to the middle point of the opposite side, right? Okay, let me do that. Suppose you take the middle point of the opposite side, and if you join this, then you can conclude that these two angles are the same. What's the reason for that? Now you've got two triangles, and you will see that these two triangles, you've got a stroke, stroke, double stroke, double stroke, and this side is a side on both triangles. It's common to both triangles, right? So it's obviously equal to itself. So you have the three sides of this triangle are equal to three sides of this triangle, and therefore these two triangles are congruent. In other words, they're identical in every respect. In particular, the angles opposite the red side are equal. This angle in this triangle opposite the red side is that one, and in this triangle, the angle opposite the red side is that one. So therefore, you have that the claim that if these two sides are equal, then those two angles are equal. So to prove that, I'll repeat, all you have to do is to split it down the middle. And what we said here was to join it to the midpoint of the opposite side. But as I said earlier on, you need not do that. You can do, just one moment, please. Sorry about that. Okay, so okay. So to split it down the middle, you can either have, I took the case where these two were equal like that, and we concluded that these two angles are the same. But instead of doing that, I could have dropped a perpendicular from here. You could have done that as well. And when that happens, again, you have, I'm not going to do it, but again, you have that the two triangles are congruent. In this case, the reason for congruency is not three sides as we had before, but this time you'll have a perpendicular here. So in this case, you have a right angle, a side and a hypotenuse condition, and those two triangles are congruent, and therefore you can conclude these two angles are equal once again. So you can either draw a perpendicular, or you can join it to the midpoint of the other side. By the way, the midpoint of if you join this line here and you join it to the midpoint of the other side, what is that line called? Anybody wants to say in the chat column? What do you call a line which joins a vertex to the midpoint of the other side? Serene, you can just tell me if anybody knows, saying something.
We have one response from Ethan. He says bisecting line.
Not quite, Ethan. Anybody else wants to say? All right, Dario, tell them what it is. It's called the median. Right? It's called a median. So
I beat me, sir.
yeah, okay. So a median of a triangle is a point, a line which joins a vertex to the midpoint of the opposite side. All right, and the line which joins it, the perpendicular line, is also given a name. This line here is called an altitude. right? So there are three medians from each of the vertices. There are three medians, and the altitudes, there are three altitudes, right? And Ethan, you said the bisecting line. The bisecting line, maybe we can call this line here, which bisects the angle. You can call it the bisecting line, but we normally call it the bisector. So the bisector of an angle is the line which bisects the angle, as the word suggests. So you can split it like this. You can split it by drawing a perpendicular, or you can join the median. In any one of those three cases, you'll have two identical triangles, and those identical triangles will have the same angles, and therefore, in particular, those two angles are the same. All right. Now, what is very interesting in an isosceles triangle is that this line, the splitting line, it does this, right? It bisects the opposite side, and these two angles are also the same. So this red line, if you forget the other two lines, that's what I've done here. You draw a line, and you take a midpoint of that line segment, and you drop a perpendicular. Now that line is given a very special name. What is it called? Anybody wants to say? Sorry, no answers?
Not yet. Perhaps they're still typing.
Okay, I'll tell you. I'll relieve you of your burden. It's called the perpendicular bisector, right? It's perpendicular and it bisects. So some genius decided to call it the perpendicular bisector, very original name. So the name already tells you what it is, okay? Now, this, given a line segment and the perpendicular bisector, a very, very important property about that is that if you take any point on the perpendicular bisector, any point like the one that I've chosen, and if you join it to the two endpoints of that segment that you started off with, these two lines are always equal, no matter where you take this perpendicular bisector. Okay, so if I took a point here, then and I join it to this, and I take the same point and join it to that, then these two are equal. Right? Any point on the perpendicular bisector is equidistant, equal distance from the two endpoints. It's equidistant from the two endpoints of the original line segment. So you'll always get an isosceles triangle created, right? And to create this isosceles triangle, all you have to do is you already got 2 points. The third point, you choose it on this line, and you have an isosceles triangle. So a very, very important fact is that in any isosceles triangle...
Sorry to interrupt you, Prof.
Yes,
there's
go
a
ahead.
question from Ethan in the chat. He asks, is there a line of proof for that property that you were just talking about, that a point on the perpendicular bisector is equidistant from the two endpoints?
Yeah, okay. All you have to do is to just compare these two triangles, Ethan, right? You got this equals this, 90, common side. These two triangles are congruent, and therefore you have all the properties are the same. In particular, that equals that.
By side angle side, right?
Yeah. Yeah, right angle. No, actually, it's two sides include an angle. Because you got this and red and 90 degrees. So this is not right angle hypotenuse side. You can, you're proving that the hypotenuses are equal. Right. So, yeah, okay, thanks for that, Ethan. Yeah, it's again congruency. Well, the three properties of this are equal to three properties of that, and therefore it's congruent. Okay, thanks for that question. Now, the important thing here is if you start off with a random isosceles triangle, this vertex here always lies on the perpendicular bisector of the opposite side. So remember that. In an isosceles triangle, the vertex always lies on the perpendicular bisector of the opposite side. We're going to use that maybe a couple of times. In fact, it's a very, very useful thing. Even in grade 11 and grade 12, when you have an isosceles triangle, you can solve a lot of problems involving an isosceles triangle by splitting it down the middle. See, when you split it down the middle, then you can get you can make a lot of interesting conclusions. All right, we are going to say some other things about that. Okay, so that takes care of triangles. And now let me just go on to, let's do the very first problem. So in triangle ABC, usually they give you the diagram, but sometimes they don't give it to you. In Olympiads, they don't give you the diagram. You have to draw it yourself. So, but in our cases, yeah, we're going to draw all the diagrams. But you need to have practice by looking at this, the description and drawing the diagram yourself. Okay, so in triangle ABC, D is a point on AC. You can see D is a point on AC such that AB equals AD. Well, we've already drawn that in. Okay. You also know that angle ABC is this angle here, starting from ABC. In other words, this entire angle here. You also know that that angle minus ACB, curl minus cross, is equal to 30 degrees. So you know that. And the question is, calculate angle CBD. CBD. In other words, this angle here. CBD. So what is that angle? You're not given any, you're given no angles. That's a remarkable thing about this. You're not given any angle whatsoever, and you're asked to calculate some angle. It looks as if it's impossible to do it because you're not given any information about what these angles are actually. Okay, so this is the power of mathematics, the beauty of mathematics, and you will see how we can calculate this angle without knowing the actual value of any of these angles. So let's give a name to this angle. Right. This is actually the beginning of something which I do very often in geometry, where I use symbols for angles, algebraic symbols, X. I mean, I don't like to work with this horrible thing here with 4 symbols. I just put a symbol, single symbol, and I know that this angle represents angle CBD. So I'm going to calculate X. Now, I'm going to give a name to this thing here also, because I know something about X plus Y, this whole angle. So let me give a name to that. But there's another reason why I give a name to this angle here, because it's part of an isosceles triangle. So these two angles are equal because this is an isosceles triangle. And now you have Y and you have X and you have dot. And you can see you've got a flag here, right? There's your flag, starting here, like that, like that. There's your flag. And this becomes the exterior angle, Y, right? And the exterior angle is equal to the sum of the interior opposite angles. So the angle next to Y is that, and the remaining 2 angles, if you add them, you must get Y. So Y is equal to dot plus X. All right? Okay, so if you make dot the subject, dot is equal to Y minus X. Okay, perhaps we shouldn't call this dot. Let's give a name to this as well. We can call this Z. So Y is equal to Z plus X. Y equal to Z plus X. So we want to calculate Z. So you can see Z is equal to, no, I'm sorry, we need to calculate X. Okay, we were given that that ABC, in other words, this whole angle minus ACB. So we are given that X plus Y ABC minus ACB minus Z is equal to 30 degrees. We are given that. Okay, so this means that I can make Z the subject again. Now remember, Z, we've already calculated Z. It's Y minus X. So why don't we substitute for Z? Then we can get rid of one unknown. One of the things about mathematics is you try to get rid of unknowns. So you reduce unknowns until such time you're only left with the knowns. Okay, and that will solve the problem. So I've got a minus sign in front of the bracket. So I'll put minus. Be careful, when you got a minus sign in front of a bracket, sign changes. So you have x plus y minus y plus x is 30 degrees. Right? Now plus y minus y goes away. X plus x is 30 degrees. And lo and behold, x is 15 degrees. We actually calculated x, right? Without knowing what x, y, and z are. Simply by using algebra. See, the power of algebra and geometry, don't separate them. All different parts of mathematics, they all are all siblings. They all get along very well with each other. So you can always help. One sibling is used to help another one. Okay, like here, algebra is used to help its sibling geometry. Okay, so let's go on. We solve this problem. And let's see what I've got in store for you after this. Okay, so we have, now I'm saying something about areas. The area of a triangle is 1/2 base times height. Okay, you all know that. Half base times height is the area of a triangle. But the area of a parallelogram is equal to the base times height. The half disappears. So if you got a parallelogram, the area of a parallelogram is base times height. Now, a particular parallelogram, which you are quite familiar with, is the rectangle. And I'm not very used to this. Okay, sorry. I had a tool which actually allowed me to draw rectangles. Let me see. Oh, yes, here it is. Okay. So if you have a rectangle is a parallelogram, right? You already know that the area of a rectangle is length times breadth, but we can use their language. Base, there's your base, times height. This is the height of the rectangle because it's 90 degrees. But what we are saying in this thing here is if you take any parallelogram, the area of the parallelogram is base times the height. So if you have a skewed parallelogram, let me just see if I can draw a skewed parallelogram here. Maybe something like this. Like that. Okay. So the area of this shape here is a parallelogram. And the area of that is, you can take any one of the sides as base. But what is the height? The height is the distance between the parallel lines. By distance, we mean perpendicular distance. All right. So we are talking about this distance here. The line which is perpendicular to both of them. From here, you drop a perpendicular, and that becomes the height. Okay, so the area of this is base times the perpendicular distance, which is the height. Like even in a triangle, when you say half base, if I chose this as base, then what is the height? The height is, you look at the remaining vertex, and the height is the distance from that to the line. But now when you draw the perpendicular line, right, you will see that that perpendicular line is outside the triangle. So the area, the yellow part is that base, and that is the height. So the area of this yellow part is half b times height. Okay, so that allows me to get on to the next problem, which is so you got this problem here. The large quadrilateral shown has two right angles. There's a right angle here. A quadrilateral is a four-sided figure, as you can see. Right? There's the yeah, so you got a four-sided figure. Oh, okay. Sorry, we got a new update on the old Zoom, and some of these things we're not very familiar with. Anyway, so if you go around this, it's a four-sided figure, there are four sides, and you got two of them are 90 degrees. And the problem is to find the area of this quadrilateral. And you're given some numbers. You're given this is 6, you're given that is 7, and you're given that is 2. But this gray shape, whose area we're going to find, is a rather weird shape because it's not a rectangle, it's not a parallelogram, it's nothing which is familiar. It's rather a kind of a funny looking quadrilateral, which has got no special property. So how are you going to find the area of this using the given information? The information being that this side is 2, that side is 7, and so on. Right? Now, see, in geometry, in most of grade 10, grade 9 and grade 10 geometry, you only study triangles. And the reason for that is because you can take any quadrilateral or any polygon for that matter, a figure which has got more than 3 sides, and you can break it up into triangles. So every polygon can be broken up into triangles. So the idea is that if you know everything about triangles, then you should know everything about polygons as well. So in this particular case here, I'm going to break up this shape by joining a diagonal, two opposite vertices. And now I've split the original quadrilateral into two shapes, right? Both of them are triangles, right? And we need to find the area of this. So if I know the area of each one of them, then I'd be able to know the area of the whole lot. So let's see whether we know the area of okay, it's not looking very good. But this triangle here, which has got a green blob in it, can we find the area of that? Anybody can tell me what the area of the green blob is? It's a triangle.
So
okay, the
no,
formula for the area of the triangle is half base times height, right? Okay, yeah. So do you know any side in this at all? In this green blob triangle? AB, that's right. So you got so let's choose this as a base. So if I choose this base, do I know the height of this triangle? You go to the opposite side angle and you drop a perpendicular, and that becomes the height. So this becomes the 10 is the height of this green blob triangle. So the green blob triangle, what I've decided to call the green blob triangle, triangle ABC, in other words, it is its area is half base times height. And to find the area of the gray part, you have to add the area of the remaining triangle. And there, again, you only know one side, namely 6. So it's half 6 base. And the height of this triangle is you go to the vertex opposite that, drop a perpendicular, and there it is. It's there glaring at us, and that is 7. So it's half 6 times 7. So when you work this thing out, you get 10 plus 21, and the answer is 31. So although this shape is rather weird, you can find the area of this because you can break it up into 2 triangles whose areas are known. Okay.
Professor, that's a
Yes,
very
sorry.
slick construction. I love it. But I was wondering, so obviously it seems like you have to make a very precise choice of triangles there. You have to draw the line AC, right? If you'd drawn BD
That's
instead, then you
correct.
don't have enough information. Yeah.
Exactly. So Dario is asking a very pertinent question. How do you know that I must draw this red line? Okay. Well, firstly, as you correctly pointed out, you can create 2 triangles in 2 different ways, right? You could have drawn this other one, and mind you, I think if you do that, then there's a problem. You could have done that. Let me just do that, and if I joined these 2 instead, so now when you try to find the areas of these triangles, this triangle, you got the base all right, that is 6. But when you go to the other side, you don't know the height from B to D. That's an unknown. So that doesn't help us. The same thing with the other one. You got a base, but you don't know the perpendicular height from D to this. So you fail with this diagonal. So therefore, you'll try the other diagonal, and then you will get to your answer. Okay? Okay, thanks for that,
There's
Dario.
also a question in chat, if I can quickly jump in again, from Jenna, who
Yeah.
asks, if you had information about the sizes of angles, could you use the area rule?
Yes. Yeah. If you know the angles, then there is an area formula. Provided you have 2 sides and an included angle, then there is a higher formula, which you normally do in grade 11 or grade 12. There may be people who are here in grade 10, so I'm trying to avoid those other formula. But thanks for asking that question. There is a third formula which you can use for the area of a triangle, and that is, if you know 2 sides and an included angle, then you can calculate the area very nicely using the following formula. If you got 2 sides and the included angle, right, then the area of this triangle is a half the product of these 2 sides times the sine, the trig ratio of the angle between them. So you could, if you knew some angles, then you'd be able to use the area formula to calculate the area of the triangle. Okay. Are there any other questions there, Darian? We can deal with the questions at the end.
Cool.
All right. Also, we can do that at the end. Okay, so let's just go on with this. So you have this new problem, which is saying that I've got a rectangle. In the diagram, ABCD is a rectangle. That means all the angles are 90 degrees. And right? And so what else have you got? You've got along one of the sides, you measure a 5 and 8. So this, in other words, one of the sides of the rectangle is 13, and you split it up into 2 ways. One is 5 units, and the other is 8. And you know the other side of the rectangle is 6. So that's the only information you have. And then what happens is you join B to this point here, which you have chosen, right? And you create a parallelogram. So these, from here you join, draw a line parallel to this, okay? And then when you do that, now you create a new rectangle. From here you drop a perpendicular, You drop a perpendicular. So you have, this is a rectangle. They say EGFH. EGFH is a rectangle. So the question is, what is the area of this green part? All right, given all this information, the 6, 5, and the 8, how do you calculate the area? All right, so that's an interesting question. So how do you calculate the area of a rectangle? Area of a rectangle is base or length times breadth. Or if I want, I like to call it base. Let's choose this as base and choose that as the height. So I need to know what B is and what H is. If I know those two, then I know the area of the rectangle because I've got a formula for it. So how do I calculate any one of these? Well, the given information, you see, it looks as if Pythagoras is going to creep in here because this thing here, opposite sides of a rectangle are the same. So this is 6. So that gives you information about this right angle triangle because this is 6 and this is 8. So Pythagoras kicks in to allow you to calculate this entire length, which is BF, right? So that's the hypotenuse, BF squared is equal to 6 squared plus 8 squared, right? That's the theorem of Pythagoras. Now this is 100. So BF squared, when you multiply BF by itself, you get 100. So BF must have been 10. Okay, so at least we know this length, but we still don't know what B is. So we need to know what that is. Because if you know the whole thing is 10, and if you know what this piece is, then you can calculate B. So let's try to see whether you can calculate this piece here. Okay. So how do you do that? Well, let's have a look at this little triangle here. Okay, and oh yes, and this is very interesting. How do you calculate B or H? Anybody has any ideas? I'll give you a hint. You use the formula for the area of a parallelogram. You can find the area of the parallelogram in this picture in 2 different ways. Okay, the parallelogram in the picture is this thing here, EBFD. Okay, so what is the area of that? Now we said earlier on that the area of a parallelogram is base. So the area of palm sometimes we say palm if we are lazy. EBFD, parallelogram, EBFD is base times height. So if you choose this as base, 5, then its height is the distance between those 2 parallel lines, and we already know that is 6. So that is the area of the parallelogram, it's 30. So we know the area of this parallelogram because we know the base and we know its height. The height is the distance between these 2 parallel lines, and it's clearly 6. But you also know the area of this parallelogram. If you choose this as your base, this entire line here, BF. So the area of this is also equal to BF times H. And we calculated BF. We used the good old theorem of Pythagoras, and we saw that that was 8. So now you have that the area is also equal to base, and the height of this parallelogram is the distance between these 2 parallelograms, and that is precisely H.
I think you mean 10, Professor, for BF.
Sorry?
I think you mean 10 for BF, not 8.
Oh, 10, yeah. Oh, okay, thank you very much. Okay, that would have got me into some trouble. Okay, so 10H, that's very much better. That's the area of this. And we already know that it's also 30. So that gives you H straight away. So that's beautiful. So we know what H is. The height of the parallelogram, if you choose that as base, is 3. So that allows you to calculate this. So this is 3. But now this little baby triangle here, you got 2 sides for it. This is 5, this is 3, and this is 90 degrees. So it's easy to see that that will be 4. Okay, so GD is 4. It's the third side of a right angle triangle. We knew that the entire thing was 10. So this piece is 4. So therefore that piece is 10. I'm sorry, 6. Because the whole thing was 10. So this is
Sorry, maybe we are skipping a step here though, because we know that BF is 10. That's what we calculated. So we need to reason then that ED is the same as BF, right?
Thank you for that. So BF, we calculated this, but this is a parallelogram, so the opposite sides are the same. If this was 10, so is that. Thanks, Darren. So is that. So this whole thing here is 10, and this piece is 4, and so that is 6. So you got, now you got the dimensions of your rectangle, and the area is length and breadth, which is 80. Okay, so you can see, although we were given some scant piece of information, but slowly we used the theory that we had that the area of a parallelogram is base times height and Pythagoras' theorem. So we used that. And perhaps some other theorems, like for instance, the opposite sides of a parallelogram are equal. These are all important results in geometry. And we use them eventually to zoom in on the problem at hand. Okay, so now I want to say something about a circle and tangents. Okay, I know the grade 10s, they probably have not done circles yet. Have you done anything on circles? Anybody from grade 10?
Asanda says no.
No, right, okay. So, but I presume you know what a tangent to a circle is. A tangent to a circle is something which touches a straight line, which touches a circle at exactly one point. See, normally when you draw straight lines, right, you can have a straight line which doesn't touch it anywhere, or you can have a straight line which touches it at 2 places. But then you have some lines which touch it at exactly one place, like this one. And that's called a tangent. If I push this line forward, it doesn't cut it again, right? So it just touches it exactly, right? So that's a very important line. There's a point where it touches it, and that point is called the point of contact. Okay, so this point here is called a point of contact, and a circle has always got the center. The center of the circle is an extremely important point. So when you got a tangent, you got 2 distinguished points. One is the center of the circle, and the other is the point of contact. Okay, now very interestingly, when you join the center to that point of contact, you get a radius. In fact, there are lots of radii, right? A circle has got infinitely many radii. You can draw lots of lines going from the center. Oh, goodness. All these are radii, right? From the center to the boundary. So this is one particular radius. Now this radius here is perpendicular to the tangent. That's what we want to say. The radius of a circle is perpendicular to the tangent at the point of contact. Now, what's the reason for that? The reason for that is a little bit subtle, but I'm going to do it very quickly. If you look at this adjacent diagram, when you join the center of a circle to any point on this tangent, right, you will see I'll get a lot of lines like this. You will always see that this line here is longer than that line. The reason is, from here to here is the radius. In other words, the same as that. But then you got a little piece extra. So you have, this is bigger than that, which is the same as that. So all these lines are longer than that one. So this particular line that we got is the shortest distance from this point to this line. And you know that the shortest distance from a point to a line is a perpendicular line. Right? If you are walking towards a wall and you want to get there as quickly as possible, and you are sitting here, right, you wouldn't want to take a long path. You would not go like that. You want to go straight, right down the middle. You want to hit it perpendicular. So this is the shortest distance, the perpendicular distance. Okay, so a radius is always perpendicular to a tangent. So this is always 90 degrees. So that's an important fact. So that's the first result of a tangent, that the radius is perpendicular to the tangent at the point of contact. Then there is another important result that I want to stress here, and that is that from a point outside a circle, you can draw two tangents. Right? From a point outside, you can draw a tangent here, or you can draw a tangent here. There are only two tangents you can draw, right? The second result is that these two tangents from the point outside the circle, they are always equal in length. This tangent is equal to that in length. Right? Right. Okay, and I want to say why. What is the reason that these, how do I know that if I got a point outside and if I draw a tangent touching it in exactly one point and another one, how do I know that these two are equal? So there is a way to do that, right? And you have to draw constructions like what we did earlier on when we were proving the theorem on the exterior angle. In every theorem, you have a construction. I better tell you that. A theorem is a theorem because there are constructions. Right? This is a very simple way of explaining which are the theorems in geometry. So these theorems, you have to know what the theorems are because you use them to prove problems. Right? Those now become known facts. So you must know the statements of all the theorems in geometry. Right? It's always nice to know the proofs as well. I will always give you the proofs, but you need not know the proofs for your purposes, but it's always nice to know the proofs. Okay, so this particular theorem says that these two tangents are the same, equal in length. So what's the reason for that? The construction is I take the center of the circle and I join it to 3 points. One is that point, the other is that point of contact, and that point of contact. And when I do that, then I get two triangles, right? And you will see that these two triangles, these are radii, so they must be equal. In a circle, the radii, all the radii are equal, because this is the center of the circle. We just said that this is 90 degrees here, because at the point of contact, the radius is perpendicular to it. And these two triangles now, if you compare them, you will see I've got side, side, angle, angle, common side. This thing here is common to both the triangles. When I say these two triangles, I mean these two right angle triangles. Right? They are congruent. And the reason for the congruency is you got the red line, and that angle, and you can see this is not an included angle. So this is your right angle, hypotenuse, and a side. They are congruent. And therefore, this side here, that side must be equal to that side. That is exactly what I asked earlier on. Is this equal to that? And the reason for that is these two triangles are congruent. In fact, you have a very interesting shape here. Whenever you got a point outside a circle, and you got the center, and you got these 2 points of contact, those 4 points, they create a quadrilateral. And here you can see this quadrilateral is a very special quadrilateral because these two sides are equal, and those two sides are equal, So what is the name of this triangle, of this quadrilateral? What shape does it have? Anybody wants to say?
Genus is a kite.
It's a kite.
Parameters.
It's a kite, right? Two adjacent sides are equal. Those two adjacent sides are equal. It's a kite. And as a result of this, you actually have you have isosceles triangles. If you join the other diagonal, which you haven't joined, right? If you join it, then you're going to get an isosceles triangle on this side, and you get an isosceles triangle on that side, right? And now it means that this point here is on the perpendicular bisector of this green line. And so is this. This point also is on the perpendicular bisector of the green line. Because we said earlier on for an isosceles triangle, that vertex is always on the perpendicular bisector of the opposite side. So these 2 points are both on the perpendicular bisector. So you can see this line here must be the perpendicular bisector. So therefore, a kite has got a very interesting property that that these are equal, because this red line is the perpendicular bisector. That's 90 degrees. So the diagonals of a kite, they are always perpendicular to each other. So that's one of the important properties of kite. I just branched off a little bit, starting off with tangents. I created a kite, but this is a very special kite, right? Because 2 of the angles are right angles, right? We'll come back to that. Okay, now so that I needed those to calculate the next problem, to solve the next problem, which is the following. Okay, you got a long story here. Okay, I'm not going to read all these. The diagram explains everything. I got a circle. I got a point outside the circle. I draw 2 tangents, AB and AC are both tangents. And then I have another point on the circumference. And at that point, I draw a tangent. At each point on the circumference, you can draw a tangent, something which just touches a straight line which just touches the circle. So I draw a third tangent. This is called, it's a tangent to the circle as well. Now, they tell you that AB is equal to 20. They give you only one side. They say this is 20. I get a very cross one, say it's 20 centimeters. Certainly isn't 20 centimeters, right? But people put on 20 centimeters. It's not necessary to say 20 centimeters. You just say 20, right? And you can decide what 20 what. You divide this into 20 equal pieces, and each one becomes a unit, and you say it's 20 units, right? Need not be centimeters or meters or whatever it is. Okay, physicists like Dario would be interested in calling them centimeters. Mathematicians don't give them any names. Okay, so that's the only information you have. And the question is, what is the perimeter of APR? Oh, that's a very interesting question. The perimeter of APR, here you have a triangle, APR, and the perimeter, now you might think, perimeter, you only talk about perimeters in rectangles, but that's not true. Perimeter means the sum of all the sides of your figure, all the boundary, the full length of the boundary. So you got a triangle here. The perimeter is, the boundary consists of 3 pieces, AP, PR, and RA. So that is the question. What is AP plus PR plus RA? And you will say, oh my God, I don't know any one of these. How the heck am I going to calculate the sum of all these? And that's the beauty of mathematics, right? The theorems that we have got, the algebra, it kicks in very nicely to solve these problems. All right. Now I'm going to work it out right here in this picture. I don't have enough space. Okay. So how do we do that? Now, the way to do this is we have absolutely no idea what the three sides are, but we have these theorems, which I just proved. This is a point outside the circle, and this is a tangent to the circle. This is a tangent. So we know that these two lengths are the same. So let's call this one here x, and this will be y. Oh, I'm sorry. That will also be x, because the tangents, the two tangents from a point outside the circle are always equal. So this is x. Okay, so those two are equal. Now, likewise, this point here is a point outside the circle, and you've got two tangents going to the circle. So both these are equal, right? So if this is y, this is y. But wait a minute, this whole thing here is 20. We've said that. And this little piece here is x. So this part here must be 20 minus x. It's the whole length minus this little thing which is jutting out from here, right? But these two add up to 20. So this has to be 20 minus x. And likewise, this piece here must be 20 minus y. Why? Because from here, these two tangents are equal. So AC is also 20. And AB is 20, AC is also 20, because the same result, two tangents from a point outside the circle are equal in length. So if this is y, that's 20 minus y. So now we need to calculate this thing here. Now, what is AP? Okay, AP is 20 minus x. That's AP. PR. PR is x plus y, because it's equal to this whole thing here, which is x plus y, plus RA. RA is 20 minus y. Okay, so now because we used symbols, we've got algebra now. Okay, minus x and plus x disappear, plus y and minus y disappear, and in the end, the only thing you're left is 20 plus 20, which is 40. How about that? You don't know any of these three, but yet you know the perimeter.
Is there time for a quick side remark, perhaps?
Yes, Dario?
This is not entirely rigorous, but I do think it's kind of beautiful. If you imagine sort of sliding the point Q towards the point B,
you'll always get the same perimeter.
Yes, but what I'm saying is, in the extreme case, if Q becomes B, then the triangle collapses down to just 2 times that line 20. So maybe that's a nice way you could see it at a glance.
Yeah, okay. So Dario is giving you a method of actually solving this problem without doing any calculations, but he's making some assumptions, namely that the guy who set the question is saying that it doesn't matter where Q is. That's what he's saying. Because we didn't say what Q is, nothing about Q. It just says any point. So then he says, why don't you make Q equal to B, right? And then you get a kind of a degenerate triangle. Your triangle is APR, so then it now becomes ABA, because you've got the Q is coming right on this. So what is the perimeter of ABA? It's AB plus AB, which is 40. So if you use the fact that this point here can be slid along here, and it doesn't matter where it is, then you say, why don't you be there? But there's no triangle. It's a degenerate case, but it's an extreme case. But that will give you an idea as to what the answer should be. Thanks for that, Dario. All right, so let's just move on. Okay, so what have I got here? Do I have a heading here? No. Okay, here I've drawn something here, which is actually the statement of a theorem. When you got a circle, so we have some grade 11 learners here, so I have to speak about circles as well because they study circles. The grade 10, you're getting a preview, a sneak preview into what you can expect in grade 11, where you study circles. So it's not difficult, as you can see just now. See, there's another theorem on circles, and that is, if I got a circle and if I've got a chord is a line which joins 2 points on a circumference. Like this is a chord. If I could take any 2 points and I will get a chord if I join them. So if I take a random chord like that. The largest chord, by the way, is a diameter. Right? The largest possible chord you can draw is a diameter. That goes through the center. So the largest chord has got length twice the radius, because you got the radius plus the radius. Okay. Okay, so if you go back to what I was going to say, what I was saying is that if you have a single chord and you got the center, now when you take the center and you join it to the midpoint of a chord, any chord, then there's a theorem which says that that line is perpendicular to the chord. So if I join it to the midpoint, take this, join it, but we don't know about the, all you know is that you have joined it to the midpoint of the chord. And the conclusion is that the angle is 90 degrees. Just one moment, please.
And so, Prof, you are muted, but while we're waiting, I just want to quickly introduce Prof. Ritu Goswami, who's also joined us. Hi, Prof.
Sorry, I was muted. Hi, hello, everybody. Hi, Pubal.
Yeah, hi. Welcome, Ritu. Thanks for coming. Okay. So what I was saying was that, when you join the center of a circle to the midpoint of a chord, you can conclude that that line is 90 degrees. You can make that as a conclusion. And the reason for that is when you join, this is an isosceles triangle. I told you earlier on, why is it isosceles? Because these are radii, and I told you if you join this to the midpoint, then everything nice happens. So that's the reason. Or for that matter, if you drop a perpendicular from the midpoint, the center of the circle, that will then bisect the other chord. In other words, if you know that this is 90 degrees, you can conclude that these two are equal. So one of them implies the other. And that comes out from what I said earlier. Okay, so let's see why we need that. We probably need that because we want to prove now we got this rather interesting problem. This is quite a demanding problem. So let me take it easy with this. What do we have here? Let me explain. A certain type of ring has outer diameter 58 millimeters. You can see this ring here. It's got a ring with a hole in it. It's like what you call a washer. Okay. So you have two circles, concentric circles, because they got the same center. And the outer diameter, in other words, if you join the outer circle through the center to the other one, that length is 58 millimeters. An inner diameter of 40 millimeters, so that's talking about the inside circle. The diameter is 40. And the thickness, so there's a thickness to this ring, and the thickness is 1 millimeter. All right, so you have a situation where you've got all these rings all stacked up here, one on top of the other, as you see. And then you take this, another ring, and you place it on this so it balances. So this ring here is sitting inside this hole. Right? It's sitting inside this hole. But it says that if one stacks enough rings, it is possible to stand another ring vertically on top of the pile, like the way it's done here, in such a way that the ring touches the bottom. This one here is touching the bottom of this. In other words, this bottom ring is on the same plane as where this thing touches. Right, so you have to sort of imagine this thing. So the question is, how many rings are in the stack when this happens? It looks as if it's an impossible problem. All you have is the diameter of the large circle, the diameter of the small circle. You also have the thickness of the rings. So how many rings are there so that this thing touches the bottom? All right, so let's go through this thing here piece by piece. The question is very important. How many rings are there? Right. So in other words, you want to know 1, 2, 3, 4, whatever. How many are there? But you know the thickness of these rings are millimeters long. So to know how many rings there are, it will be nice to know what's the distance from there to there. In other words, if I join this to this, how far is it? If it was 5, then it's 5 millimeters, it means there are 5 rings. So instead of counting the number of rings, you might as well count the distance from the top there to the bottom. Now, how the heck are you going to do that? So now you have to look at this circle. This thing here touches look, this demands a lot of imagination. It's touching it here somewhere. Oh, I'm sorry. It's touching it there, and it's touching it there. Right? Okay, and when you join these two, these are points of contact here. When you join those two, I think it's not difficult to see that it has to be the diameter. It can't be sitting on a small chord here. Otherwise, it will topple over. It has to be sitting. So this thing here is a diameter. When you join these 2 points of contact, is a diameter of the inside circle. Right? And then you have, from this point here down to the bottom, it's 6. So from here down to the bottom, from this line here is horizontal, right? It's the same. It's kind of parallel to the plane on which this whole thing is sitting, and that we need to calculate the distance from this line here to the bottom. Okay, so that is a little bit complicated, but I'm going to model it, and you will see in the next diagram what's going on. So that is what I've got. So I've put everything on a flat sheet of paper. Now this is where these two things meet. The point of contact. And we said that this is the diameter of the small circle. So this thing here, the diameter was given as 40 of the small circle. We know the diameter of this large one is 58. Those two numbers were given. Right. So we already know that these are all 1 centimeter long. So you want to know how many centimeters. So that's the question. So how do we do that? Well, to get this what I can do is join the center of the circle to the point of contact where that ring touches the table. I'll call that the point of contact, and I can join these two. So now we need to find out what the length is from here to here. Now that should be, we're getting there now, because we know the full length. Full length is the radius of the large circle. And the diameter of the large circle was 58. So the radius of this is half of that, which is 29. So we know this, we know from here to here, it's is 29. And we want to know what this is. So this becomes an interesting problem. Okay, but now we also know that this radius is perpendicular to the tangent, and these are parallel. So you have, that must be 90 degrees also. But now we have the center of a circle joined to a chord, to a point on the chord, and it's perpendicular to it, right? And I just told you that when you have that situation, then this chord is bisected. These two parts will be equal. But we know the full length of this chord is 40. So let me just take that 40 out from where it is. And I'm taking the whole thing out. So I'm going to go all the way there. And I know that from here to here, the whole thing is 40. So from here to here, it must be 20, because this perpendicular line bisects this chord. Right. Now, where do we go from there? This is 90 degrees. We're trying to calculate that one. We know the whole thing is 29. So it'll help us if we know what that is. So what is this? But this is the side of a right angle triangle. So let's join, let's complete the triangle. And you see that when you complete it, the third side is actually a radius of the large circle. So this is 29. So now we are nearly there. So we are nearly there because we have a right angle triangle with two of the sides, right? So from here, we can calculate that one. And from that one, we can calculate that one because the whole thing is 29. So we can calculate that. And from that, we can calculate how many rungs there are. So this is an interesting problem where we work backwards, eventually to come to something that we can actually calculate. So if we call this thing here x, for instance, then by Pythagoras, this is x squared is equal to 29 squared minus 20 squared. You don't need a calculator for this because this is well known. It's a difference of two squares, 29 minus 20 into 29 plus 20. A lot of you will run rough to a calculator and find square roots. No need for that. This is a squared minus b squared, a minus b into a plus b. You have 9 times 49. So that's very nice because the square of x is 9 times 49. So x itself must have been 3 times 7, which is 21. All right, so this is 21 here, which means the whole thing is 29. So it means that this must be 8. And therefore, the answer is each 8 rungs because each rung is 1 millimeter long. Okay, so that is quite a demanding problem, but you will see that if you break it down slow by slow, you can actually get to the answer. So don't be put off by this. It's one of the more difficult problems that is usually given. But I'm simply illustrating to you that even these difficult problems, they can be broken down into simpler units. Okay, so I've redone all these things. Yeah. So let's just. Okay, now we're going to go on to polygons. Whether you say polygon or polygon. If you ask a layperson what is a polygon, he'll tell you it's a dead parrot. Got it? Polygon. Okay, so in our language, a polygon is a figure with all straight lines as the edges, right? It's a generalization of a triangle, a quadrilateral, a pentagon, hexagon. All these things are polygons. Now, there are some important facts about polygons which you need to know. The sum of the exterior angles of any polygon is 360 degrees. Now, that's a very interesting fact. I'm not proving it, but what we are saying here is that if you've got any polygon, and if you draw the exterior angles for that, and if you add them all up, then you are going to get 360 degrees. That's quite remarkable because it doesn't matter what the polygon is. I'm not going to draw it very accurately. Right, so if you take any polygon whatsoever, and if you extend them, exterior angles, but you must extend in the same direction. Go down like that, and from here you go that way, 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 right? It's like making a full revolution, see? And that is why when you add up all these things, you're going to get 360 degrees. So if you add up all these exterior angles, these are called exterior angles, you get 360 degrees, right? Now, generally, the polygons which are of interest are what you call the regular polygons. Now, what is a regular polygon? A regular polygon is a nice polygon. It is where all the sides and all the angles are equal. So a regular polygon is a polygon with all the sides and the angles equal. Okay? So, for instance, if you take you take a square, is an example of a regular polygon because all the sides are equal and all the angles are equal to 90 degrees. So a square is the only four-sided regular polygon. You also have regular triangles. All the sides and all the angles are equal. And that, as you very well know, is an equilateral triangle. And you have, so like this, you have regular polygons, regular hexagons, regular pentagons, and so on. Right, so now this problem here is, and each exterior angle of a regular polygon, of any regular polygon, you can calculate the exterior angles. But I'm looking particularly here at the exterior angles of a regular octagon because that is what I need to. The next problem deals with that, right? Each angle of a regular octagon is 45 degrees. Why? Because when you add them all up, you get 360 degrees, and they're all equal, right? Because all the interior angles are equal, and therefore the exterior angle must also be equal. So you divide 360 by 8, you get 45 degrees. So all the exterior angles are 45 degrees. So the interior angles will have to be 135 degrees because the exterior angle plus the interior angles are supplementary. Okay, so that takes us to the next problem. Okay, and I don't have much time. and I have quite a few problems. I'm still only halfway through. Okay, so I've taken far more. I've done far more than I was supposed to do. I didn't want to rush through it. Serene, what time shall I stop?
So we will be stopping at 11 today. So
Okay.
it might be nice to wrap up a few minutes before, and then we check if there's any questions.
All right. Okay. 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 Now, one of the things about regular polygons is let me go down this thing here because I want to say something. There are some other circle theorems which I mentioned later on, and one of them is equal chords subtend equal angles at the circumference at the center actually. So you got equal chords. When you join the endpoints of a chord to the center, then you call this angle here the angle which is subtended by the chord at the center. And these angles here, the subtended by the chord at the center, they are always equal because these two triangles are congruent, right? And those of you who have already done some circle theorems will know that the angle at the circumference, if I join the endpoints to a point on the circumference, that angle is equal to one half the angle that it subtends at the center. That's a very important theorem in geometry, that the angle subtended by a chord at the circumference is equal to one half the angle subtended at the center. So that alpha is equal to one half this angle, which I'm just drawing. So if these two angles are, if two chords are equal, they subtend the same angle to the center, so therefore they will subtend the same angles at the circumference. So that's a very useful thing to know. And also, a cyclic quadrilateral, I just want to say is something, sorry, I'm sort of rushing through this now because I don't have so much of time. But when you look at it, there is always a circle that passes through the vertices of a triangle. So if you've got a triangle, you can always draw a circle which goes through the vertices of the triangle. And it's quite easy to find out what the center of that circle will be. Okay? Because the center will be equidistant from, you need to find out which point is at the same distance from the three vertices. That will have to be the center of the circle. So how do you find the point whose distances from the three vertices are the same? But then you will say, but this, if these two are the same, this point must lie on the perpendicular bisector of that chord. I said that earlier. So this point here lies on the perpendicular bisector of this chord. It also lies on the perpendicular bisector of the second side. So where these two meet, that must be the center of the circle. So there is always a circle which goes through 3 points, but that is not true for more than 3 points. If you got four or more points, you need not have a circle that goes through all of them. And if there is a circle that goes through all 4 points, you call it a cyclic quadrilateral if there are 4 points. Generally, you'll call it a cyclic polygon. Now, the reason why I'm saying all this at this stage is that a regular polygon is always a cyclic polygon. There's always a circle that goes through all the vertices of any regular polygon, right? In other words, when you got a polygon where all the sides and the angles are equal, all the points always lie on some circle. It doesn't happen with general polygons. If you have a quadrilateral, right, for instance, you need not have the 4 vertices sitting on the same circle. So to go back to our problem here, what we are saying here is that, I'm taking the quick way out, you've got a circle. This is regular, so there is a circle that goes through all these, right? So the question now is, what is this angle equal to? All the sides are equal. If you take this point and join it to this, come back to this, what is x equal to? Right? And the answer to this question is, you will see that x, if I join this point here, right? So you'll see x is made up of three angles. This one, that one, and that one. And these three are subtended by these three lines. Now think of a circle going through the whole lot. So this becomes a chord of the circle, this becomes a chord, and that becomes a chord. So equal chords, right, subtend equal angles at the, this is also a point on the circumference. So equal chords subtend equal angles at the circumference. So what we are saying here is that that angle is the same as that angle is the same as that angle. And if you look at all these, you'll see that there are 1, 2, 3, 4, 5, 6. There are 6 angles which are all equal. If I join this point to the other 2 vertices, then you will see what I'm talking about. Okay, so if I join this to that vertex, I can't pick it up. And this is already there. You got 6 of these angles are the same. And therefore, but they all add up to 135 degrees, as I told you earlier on, right? Those are the internal angles of an octagon, 135 degrees. These 6 equal numbers add up to 135, right? And therefore, these are all equal because they're all subtended by the equal chords. And all these points lie on a circle. So 3 of them, they make up x. So that will be equal to half of 135. So x is equal to 135 divided by 2. And that is 67.5 degrees. Okay, I had other ways of solving this problem, but this way I was able to also state some of the results that I had on circles. That equal chords subtend equal angles at the circumference and also at the center. Okay, so let's get on to the next problem. So here you've got 3 circles are inscribed in an equilateral triangle with sides of length 1. All right. Each circle, as you can see, all these circles sort of touch each other. The only thing you know is that this is an equilateral triangle, and all the sides are equal to 1. That's the only thing you know. In other words, that is 1. And the question is, find R. Okay. Now, in problem solving and in mathematics, one of the goals is to try to get an equation which involves an unknown. So I got an unknown, which is R here. Can I get an equation which involves R? Then I can solve for R. So I need to find the radius. The question is calculate R here, as you can see. Well, to this end, what I would like to do is join these 2 centers. And when you join those 2 centers by a straight line, and well, I do know that this is a tangent. So I do know that this is 90 degrees. Likewise, when I join this, it's also 90 degrees. And now if you join these two, they will go through the point of contact. So if you join these two, it goes to the point where they touch each other, right? If you want to prove that, you draw a tangent at this, and you will see that you got 290 degrees. So this becomes a straight line. So you got R here, you got R here, and now these two lines are parallel because they're both 90 degrees here, and they are equal because they are both are radii. All these they all got radius R. So this is a rectangle here. So therefore, this now we've got a certain piece of this rectangle, which is equal to 2R. So now we're getting there. We got 2R. If we can calculate that one and that one, they both are the same, as you can see by symmetry. So then we have an equation involving R. Now, how do you calculate this one? Right? Now, just concentrate on what I'm saying here now. I'm going to try to say this slowly. Here you got a point outside the circle, and you got two tangents, which is coming down. And we've seen this scenario before, and what we actually saw was that when you join this thing here, right, then these two are equal. Right? But one important thing is that when you join, you're going to get a kite here, if you remember. But now you're going to cut a sort of tiny-ish kite. Now this is 60 degrees. Now remember that these two are equal here. When we had that kite, we saw that these two triangles were congruent. So the whole thing is 60 degrees. So each one of them must be 30 degrees. So what you have here is that this angle here is 30 degrees. So you got a right angle triangle, right? And you got R here, and you got 30 degrees, right? And you can use trigonometry if you like, but even without trigonometry, you can still prove that this thing here is R times √3. And I'll show you why in this picture here. Just one moment. Even without trigonometry, you see, you got a 30-degree triangle. This is the triangle that we've got, the little baby triangle that we have earlier on. That one, you got a 30 degrees, and you got an R here. And I said that this is R times square root of 3. The way to do that is to flip this triangle around to the other side, right? And then you have this 90 degrees here, you see. So you can flip it around, and then you got R here. And these are two 30 degrees, so you got 60 degrees. So this is an isosceles triangle because these are exactly the same, right? But this is 60 degrees. So therefore, it's an equilateral triangle because all the angles are 60 degrees. This is 2R. So therefore, these are 2R. And by Pythagoras, you got 2R, you got R, and you can calculate 4R squared minus R squared is 3R squared. So you get that this is 3R √3. Okay. So I messed up my figure here. Right, okay. So you got R √3. So all three sides, when you add them, you got the equation that we are looking for, namely 2R plus 2R √3 is equal to 1. And that allows you to calculate. If you add up all the three things, you got 2R in the middle plus 2R times square root of 3 is equal to 1. That's the equation that you're looking for. You can take out R as a common factor. R into 2 plus 2 √3 equals 1. And then you can make R the subject of the formula. And that gives you the value of R that you're looking for. All right, so I'm going to, I've got 6 minutes left here. I don't want to rush through anything. Let me just see if there's any other important thing that I want to say. All right. As you can see, I try to cover up as much things as possible here. Fortunately, I went through all this. And then I said some things about cyclic quadrilaterals, and I had some nice problems on quadrilaterals. All right, let's stop there. Those last two problems, or last three problems, are rather advanced problems. I think you had enough for 2 hours. You patiently sat and listened to me, and I thank you for that. We went through quite a lot. As you can imagine, we've got maybe 3 years of geometry, and I tried to do that in 2 hours, which is almost an impossible task. But I tried to do as many things as possible within this time, so that I'm sure some of the things that I've said you would have understood and at least try to remember them. Thank you. Over to Sareen.
Thank you so much, Prof. It was a wonderful session. Just to respond to one of the questions that was in the chat box, to respond to it publicly, the recording of the session will be made available, and this typically gets added to the NETEX YouTube page. I do have your email addresses since you have indeed registered. So what we could do is, as soon as it's available, I could send out an email to you. And if there's any notes or questions that Prof. Pubalan would like to share with you, I would also send that to you via email. Don't forget that we do have a session next Saturday. So you can join myself as well as Professor Rituparna Goswami next week, Saturday, same time at 9 a.m. So even if you are not part of the juniors, but you still want to join to learn and have some fun, please feel free to do so. So we are running a session for juniors. If Dario is available, then he might be there too. So let's quickly thank Prof. Pubalan Pillay, Dario, for making the session so interactive. And I look forward to seeing you all next week. So it will be another fun session with Prof. Ritu Goswami and myself. So thank you to everybody who had joined.